Zoom recording. Welcome everyone. It's good to see all your names in the participants list and so many familiar friends of ours. Thank you for coming to our first Tech Talk. We're really excited to have David Ewing here to talk about his creation, the CodeBot. Before I get into that, know that if you need any more information, you can either email me. My email is in the registration that you got, or go to our website, furialabs.com. Also, if you are a teacher and you want to know more about CodeBot for your classroom, and you are listening to some of this with the text and the schematics and such, and it just feels very overwhelming, understand that this is a completely different webinar than the ones I've been doing for classroom teachers. So this is going to go into the engineering and design of this, which is great to learn about, but don't think that you have to understand schematics in order to successfully teach the curriculum surrounding CodeBot. We do have many summer professional development opportunities for learning more about CodeBot, as well as our Jumpstart Python with Microbits classes. You can go again to furialabs.com and see our summer schedule there. I'm going to be doing a lot of marketing very soon on that. There's also the Emphasis Pathfinders in July. We've been marketing that a lot as well. So if you want to take some time this summer to go through the whole curriculum, learn about assessment and classroom management and things like that, those opportunities are available to you. Okay, so for the nitty-gritty housekeeping, we're going to ask that everyone leaves their video and mute yourself. Turn your video off and mute yourself, because we do have quite a few people registered and we want to make sure the video doesn't lag. If you have questions, just type those in the chat box. I'll be monitoring chat throughout. So if there's something that we need to stop and discuss a little bit deeper, then I'll make sure David is directed towards your question and we answer it. But there will also be a Q&A at the end. So if it's something that's just more general, you can save that for the end and then ask him then. And of course, you can always contact any of us by email or call us if you have any other questions. If there's nothing else, with no further ado, David, I'm passing it off to you.
All right, awesome. Can you hear me okay? All right, good. Yeah, Amber, jump in there if things get weird and you can't hear me or something like that. So thank you so much, everybody, for tuning in. And yeah, like Amber said, we're going to get pretty deep. I'm not going to assume everyone is an electrical engineer. That is my background, so I have an excuse for understanding some of these things. But I do think that everyone, including a lot of students, can jump in and actually figure a lot of this stuff out. And one of the things we really wanted to do throughout CodeSpace and all of our products at Furia Labs is make sure that there's a lot of depth, you know, that we provide that pathway to learning as much as you want to learn about this, and hopefully tantalize some people into really getting into it, because that's how we feel about it, right? We love this stuff. So anyway, okay, I'm going to look over here. I've got the screen that I've shared over to my left, so forgive me for looking a little bit away from the camera. Hopefully you won't look at me anyway, and we'll just look at the content. We're going to start out by talking about why we put the things we did on CodeBot. So what is this stuff? And then we're going to jump in pretty quickly to going through the schematic diagram, which we've just recently posted up on our docs site. So you'll be able to, so a schematic diagram is the drawing that engineers use to describe all the components and how they're connected together on a circuit board. So I'm just going to show you everything that's on the CodeBot. So every one of those little black boxes and those little components is on that schematic. We'll delve into the software too, right? All of the bits of hardware are controlled by software in the system. So if you've gone through Python with robots or through some of it, you've been using this module called BotCore that you can import from your Python program, and BotCore gives you a nice little abstraction layer on top of the hardware that's on the board. So we'll talk about BotCore just a bit, kind of to show how it connects over to the hardware, and then we'll give an example or two about how you can sort of start creating your own things with the expansion connectors and so forth. So I'm hoping to leave a decent amount of time for Q&A. So I'm going to hopefully not rush too quickly. Also, Amber, shout at me if I'm really going too fast. But I have I usually have the opposite problem, right? Well, not that I don't go too fast, but I use up all the time. So I don't want to use up all the time for Q&A. And if we do need to, if you've got extra questions and we need to go late, we can. Okay, so first, the motivation, right? And some of you might have read down at the bottom of this page, and by the way, we'll share these slides with you guys after the presentation. The bottom of this page is a link to a blog post that we did a while back that was like, why another robot? You know, aren't there enough educational robots out there? And you know, we feel the same way. You know, going to ISTE and seeing all these things, you know, it's like, well, man, isn't there just one that would do exactly what we want, to load Python on it and be low cost and not look like a toy? I didn't put that on there, but there's another thing we wanted to, you know, to actually be a real circuit board that was like an Internet of Things device. Couldn't really find something out there that met all those criteria. So we wanted to focus on coding, not focus on building the mechanical parts of it. Of course, you can do that, and heck, if you have a 3D printer, you can add a lot to CodeBot, really. But it's not built, you know, to focus on gear ratios. It's more about what can I do with software. Obviously, we want to run Python through our experience with the microbit, which we loved and had great experiences in the classroom with microbits. We also found that, you know, if your Python program gets very big, you start running out of room. This microbit only has 16K of RAM in that little Nordic part on the board. And if you start bringing in other peripherals and things like that for a robot, you very quickly run out of space. So your choice is take some stuff out of the MicroPython runtime, or get a bigger processor and with more RAM and flash. And so that's what we did here. We've gone from 16K on the microbit to 128K on the CodeBot. So it's a lot more room and a lot more powerful processor in general. Low cost, obviously important. We want to be able to have, you know, as many, one-to-one is great, you know, but as many bots as you can for a classroom so that you can have close to that anyway. That's one of our sort of foundational beliefs is that coding is more kind of in some ways like math, you know, in some ways like writing. Like, you know, if you're writing an essay, well, you don't really get as much out of it if you don't make the mistakes and then have to correct them and things like that. So, so that's part of it. And then microcontroller based was important to bring out too, because, and that's what we'll be talking about in the schematic. You'll see that we're using this microcontroller, this STM32 ARM processor, and why not just drop a Raspberry Pi on this thing, you know, and run Linux, and it can run Python and all that stuff. And so there were some reasons for that, and I've listed them here. You know, underlying complexity being low, you know, something that's easy to configure. When you hit play on the, you know, on CodeSpace, it's really nice that you're pretty much erasing any part of Flash that matters, that changes, you know. So if another kid gets that, another student gets that bot or something, they're, you know, when they hit go, it's new for them now. So Linux has, while we love it, there's also a lot of sort of maintenance issues potentially there. Also the idea of it being an Internet of Things type device, you know, the bot can run, if it's just sitting there, it's, you know, it's using very little power from the AA batteries, unlike a Raspberry Pi, which couldn't run very long on those batteries. So we can talk about that more maybe in the Q&A, but, you know, this is running a low power processor that can, you know, run down like at a milliamp of current draw. So it could run for a couple of thousand hours on the AA batteries, you know. Of course, if you're running it around on the motors, you're going to not get that much time out of it. But anyway, that's another neat thing. So we definitely, as we set about to decide what was going to be on the bot, we thought first about the curriculum and about the projects that we wanted to be able to do, you know, and we wanted a compelling set of projects that you could grow with, that you could do, you know, as much as a student would ever want to learn about coding and maze solving and all kinds of things, you know. So we wanted to have a lot of room for different projects without adding so much that we added to the cost too much. So that's so it's built in. That's why we have the peripherals that we do. Okay, so I'm going to go from there to talking about, well, the pieces of documentation we're going to be using today in the tech deep dive here. I said the bot core module, and those modules that are documented that we have on our docs.furylabs.com, which we'll be going to in just a second. Those are up there on the web for you. There is also source code behind the Python modules that we use. So if you wanted to know what is behind bot core, at least at the Python level, you can see that. And so we'll be looking a little bit at that because a lot of it just sort of stops there. I mean, we're controlling the hardware directly from Python. And you wouldn't have to use bot core. You know, if you were doing an advanced class and you said, hey, you know, student, I want you to learn how to drive these motors from a Python program without using bot core, that'd be an interesting assignment. You know, they could certainly do it using MicroPython's ability to change, you know, to set port pins and PWM and things like that. And you'll see, if you look down in bot core, you'll see that's exactly what we're doing there. So there's all kinds of, we've talked about a lot, you know, you could easily do college courses with this, and you could do, you know, you could teach a lot of higher level things than we normally aim to teach with CodeSpace. So it's kind of the epitome of a high ceiling, I think. So we'll also be pulling out component data sheets, like all the parts that are on the board. When you see them called out on the schematic, you can Google search for them, and voila, there's the vendor's website or distributor's website where you can download data sheets, so you can get all the nitty-gritty information about all those components. I have a few of them pulled up here to look at. And then MicroPython underneath, you know, what we're running here is what's called MicroPython, right? Which is Python for microcontrollers, based on pull up, you know, Python, I think 3.4 is where they hit. And we're on nearly the latest version of MicroPython. We're at 1.11. 1.12 is out now, but it's really close. And the docs are up there for that. And it is, you know, some people have asked, well, wait, this is not real Python, this is MicroPython. No, it's real Python. It's exactly the same. In Python, you know, if you're doing Python on a server or Python on the cloud, the core language is the same. You know, what matters really for a particular application is which libraries you can pull in and what you're doing with it, right? So if you're running it on the cloud or doing some machine learning thing, you're interfacing with different sets of libraries than if you're doing it on a desktop or if you're doing it on a piece of embedded hardware. So MicroPython is full Python that's got libraries for the embedded side of things, and it's built to run on those sorts of devices. So let's see. All right, that's a preview. That's foreshadowing. Let's switch over to. I'm going to start by switching over to CodeSpace. And I brought it up to the page where the students in the very first project, you know, we kind of introduce them and get them connected up and write their first line of Python code to blink an LED. But importantly, we show them around. You know, what are these things on the board? Amber, give me a thumbs up that we're seeing this okay. That come up? All right, good. And Amber, it's Amber's fault that like all of these little black boxes are tagged, because initially I thought, well, the accelerometer, they need to know what that is, you know, and they need to know the CPU. But you know, they don't need to know what these little guys are. That's not that important. And Amber's like, wait, what are those? Students are going to ask. So we ended up putting tags on those things too. These are the LED drivers. So these two chips are actually the same part. And there's a 16-bit shift register, and we'll actually pull up the data sheet here in just a minute for these guys. So that's what those are. You know, the switching power supply, we didn't originally have that documented, but that's what that and the little inductor that goes with it. We'll see that on the schematic in a minute. So everything's on here. It's kind of pointed out as we go through, and I'm going to sort of show you around. I mean, the proximity sensors. A lot of you've already seen this. Expansion headers. What else have we missed? The emitter for the prox sensors. So it sort of shines out. It's sort of the flashlight, the headlight. And then you've got your two prox sensors here, left and right prox sensors, and the 5 green LEDs in the front. They're just indicator LEDs that we call the line sense LEDs, but they can be used for anything. They just happen to be lined up directly on top of the line sensors. And the user LEDs that can display 1 byte worth of information, but it's also completely user programmable. You know, on-off switch up here. The speaker and a little transistor that drives the speaker. It's a little FET. We'll show that on the schematic in a second. Let's see if we go to the next page. We've got the motors, left and right motors, and we'll talk a little bit about those as well. The wheel encoders, which is an important feature to have on this. I mean, it allows us to do really cool things like teach the students how to build their own servo, essentially. You know, how to do a feedback loop and do engineering sort of control loop, you know, a real control loop, which is actually something I've never seen done really on a, you know, this kind of level. It's really cool when you go through that project, I think. The battery pack, we actually get it. There's a diagram in CodeSpace later on about how the battery pack works. You would think these batteries are in series, so they're all lined up one at a time like that. It's actually not how this battery pack works. I didn't know that until I did that part of the lesson, and I didn't fake it and say, well, no, it's just lined up all in series. We show the real way that this one's wired up. So it's kind of interesting. I think that's maybe in project 7 or 8. And then the line sensors on the bottom. So that's kind of a tour of everything there. So I'm going to stop with the line sensors, and I'm going to use this as our jumping off point to talk about how would a student's journey go from maybe understanding the line sensors, wanting to know a little bit more, to needing to look at the schematic? Obviously, if you're going to do an expansion board, your own expansion board, which is an awesome thing to do, you'd want to look at the schematic. But let's take another approach. So let's say they're in this fence patrol project, and it's really cool because we show you, kind of a close-up view of what that line sensor looks like, and it's got an emitter LED, and it's got a photo transistor in there, and there's a picture of them, and then there's an API that you would use this thing from BotCore. So if I clicked on this BotCore docs link here, which most of our our API stuff has this little linky to our docs.ferrylabs.com, and this is where in our BotCore library, this is where we talk about line sensors. So if I was to click over here on the left, so this is the top level of BotCore. So it's got everything, the LEDs, this expansion header, speaker, buttons, proximity lines. So there's line sensors, great. So if I click on that, now I'm down here to the line sensors. So there's an API, I can calibrate them, I can check the sensors and things like that. But if I go look at this, click on this source link and look at the source code for line sensors, well, now this is showing you the source code of BotCore. The BotCore comes pre-installed on CodeBots, but you could copy this code out, rename it, copy it over to your, load it up in CodeSpace and save it to your bot and make your own changes to BotCore. You can do your own special version of BotCore if you wanted and extend it. And so you could make it my BotCore, and you could import my BotCore and then have a special version. So just as a look into it here, and these are classes, and we don't, so far in the Python, our intro Python stuff, we decided to not introduce classes yet. We're doing more kind of procedural programming, but we make use of classes. So the students aren't writing them unless they get a bit more advanced. Certainly there's nothing stopping you from doing that, but we're not teaching it just yet. But we're using classes, and so in this case, when I create a line sensors object, which if you go to the bottom of BotCore, which I'll do just real quick here, you'll see that all of these core objects, like line sensors here, are instantiated. And so if I say botcore.ls, or if I do from BotCore import star and just say ls, well, I'm using this line sensors object. So at the beginning of time when we import BotCore, this line sensors gets instantiated here. That object gets instantiated, and so this little constructor runs, this init function runs, right, our method. And one of the things it does is it creates these pin names, 0 through 4, so the 5 line sensor pins, and it creates them using an ADC object, analog to digital converter object, and it's mapping. This is kind of a nested thing here, right? It's using pins from MicroPython, the MicroPython machine library. So up at the very top of BotCore, we are importing the pin and ADC objects from MicroPython. And that's another level you can go down and take a look at the MicroPython documentation, and which we've got linked here. So if I wanted to go look here, go to the machine library, yeah, go into machine. And so I know I'm at 1.11, so that's good. So here you can see a few different functions, but also objects like the pin object or the ADC object. And on a pin object, I can create it, and then I can set a value high or low, or I can read that pin as well, read the value of that pin. So back to our line sensor things. Okay, so I see that in line sensors, a second, get back there, BotCore, line sensors. I promise you we're drilling into the schematic here. So so line sensor 4 says it's connected to pin CPU.C0. So I've got C0, 1, 2, 3, and A0. So to know what that is all about, I'm going to go to, if I go to docs, over here we've got the schematic and expansion connectors. So the schematic is linked, there's a PDF linked as well as pictures of the schematic. So I'm just going to flip over to the PDF. All right, so what was that again? So line sensor, so PA0 is line sensor 4. PC0 is line sensor 0 sense. So let's see if that looks the same as what we were seeing. Sorry for jumping around on you a bit, but this is, I figured this would be a good way to kind of connect the dots between your code and the schematic. So yeah, so LS4 is supposed to be CPU C0. So let's take a look. So CU0, line 0 cents. Okay, all right. On the and that's actually showing you one of the interesting things in the code. Because the PC board on the top was labeled 43210, actually reversed of what the schematic is. So they're actually reversed in here. But these are the 5 line sensor lines here. So the schematic is correct, but the bot core library named them differently because the silk screen of the PC board didn't match what the what the wiring on the schematic. So it's something good to note if you're looking through the schematic. But the bottom line is definitely, you know, they're lined up here so that you can access them from MicroPython, and that's where they sit on the STM32 processor. So that brings us to the schematic, and we are looking here at the at the main CPU. So this STM32 has all these port pins, port A, B, and C. 1 or 2 pins of port D are brought out. There's a crystal that actually controls that, gives it the clock to run the code, right? To run it. So CPUs run on a clock, and this one's is multiplied up to I think we're running at I meant to make a note of that. What frequency we're typically running at here? So it's probably right around 30 megahertz is what that's multiplied up to, but it's variable. We can change the clock frequency multiplied from this 32 kilohertz resonator. We talked about the line sensors coming in. Let's move on to these pins right here. The motor left, right. You've got 2 N pins and 2 PWM pins. And actually, I'm going to jump over somewhere else real quick first. I've got the STM32 data sheet brought up. So the STM32 processor that we're using, you can download this data sheet. It's an STM32 L476. L means low power. So you can kind of see a lot about it here and get into the details. But there's a whole lot to look at. I think if we get down to one page that's kind of neat because it's got a big block diagram of everything, which will be impossible to read, but you can kind of see there's a lot on this chip. So here's our RAM and our flash, and then all these port pins, IO port pins, and then some built-in peripherals like UART, which is a serial port, universal asynchronous receiver transmitter. We'll talk about I2C and SPI buses and things like that, but all that's coming out. And many of these pins are brought out and used on the, we're using just about every pin on that processor, and then some of them are brought to the expansion connector as well. So that's the STM32. So kind of moving over, we'll say, okay, let's go next to the upper right-hand corner of the first page of the schematic. This is the motor controller, what's called an H-bridge. It's a dual H-bridge controller for those 2 motors that drive the CodeBot. And so from the processor, we've got left and right PWM, which PWM stands for pulse width modulation. You can look that up on Wikipedia. I was going to bring it up, but it's going to take way too much time. But it gives you a way to vary the duty cycle from 0 to 100% of on time of a pulsed waveform, and that's what allows us to vary the speed of those motors. N1 and N2 on these guys, each one of these H bridges really controls whether you're going forward, going reverse, or one or the other of the wheels is turning. And I'll show you that. Actually, we have that brought up here. So this is this little Toshiba dual H bridge part. And if you look at so here's how it's kind of internal logic is shown. And then there'll be a truth table that'll show you. Here it is. So if you say bring N1 and N2 high, then you're going to be in braking mode, and so here's how here's how you can make it go counterclockwise, clockwise, stop, stand by, that sort of thing. And it sort of shows you diagrams. It's really neat, kind of instructive looking at this. If you want to, the students wondering, how do you get power to the motors? How is this computer controlling power to the motors? This shows you how it's done through these little MOSFETs in here. So you have to learn a little bit about FETs and switching, but once you do, then it's a really neat logic exercise to see how that works. So going back to the schematic, so that's the motor controller itself. If you look in code space, it's interesting. The motors that we're using, these little yellow gear motors, are very common. They're called TT motors. And they're available from China, from a lot of different sources there. It's weird, I couldn't find an exploded diagram of one of them. Like, what do they look like inside? So CodeSpace is one of the few places that you'll find, I think that you'll find that. I found it nowhere out on the web. So I think if you're in our Time and Motion project, where we actually go to the motors, this neat little picture of the gear motor internally, and it's actually lubricated in there. There's a little, it looks wet, it is. It's kind of cool, but I took one apart and took pictures of it so that, you know, there's nothing hidden, right? There's nothing up our sleeve. It's a little plastic gear motor. But these are actually great little motors. They're low cost and they work well. So that's what's the M here, M1 and M2 are the motors that plug into those connectors. All right, so the speaker is really simple. The speaker is just a little MOSFET. It's an N-channel MOSFET, which means when this line here, speaker PWM is high, it turns on this transistor, which means the speaker is connected to battery voltage. You're gonna get a loud click if you just connect that on. And so we would PWM that from the PWM line, which is, you can look in BotCore and verify that PA5 from the processor is the one that we're PWMing from MicroPi. You can do, that's actually also there's a DAC peripheral, a digital analog converter peripheral inside the STM32 that's also connected to that, or is able to connect to that pin. So you could play music or voice really nicely. You could do polyphonic music out of the speaker. That way, using the DAC or playback voice samples. You can also do PWM based DAC. So there's a couple of different ways you can actually make really nice sounds out of this thing. Currently that's left as an exercise to the reader to do that, because we're just playing tones with the PWMs right now, but it'll be fun when we get around to doing that. We'll talk about the debug and the STM32 debug connector, as well as the UART connector here. I've got a couple of slides on those. So those are typically not loaded. You know, there are these two connectors. Hey, I've got a camera, so if you're seeing me out, got these two connectors that are not loaded here, just 6-pin headers. But they are useful, and I'll show you why in a second. This little circuit is all about button 0. When you hold it down, it'll actually on reboot, it actually ties it activates the internal bootloader on the STM32, so you can do an upload over USB. And one of the cool things that the STM32 supports is what's called USB DFU, Device Firmware Update, which is actually a USB standard. It's not an STM32 thing. It's a USB standard. There are kind of few vendors that support it, but that's how our CodeBot firmware uploader, if you ever have to put brand new like firmware, which is rare, but you know, when we do launch new features, we'll put out a new firmware image, and it completely replaces what's on that STM32. So there is no bit of software that can't be replaced by using that DFU firmware updater, which is really kind of a cool thing from an engineering standpoint. A lot of times you'll put a unit in the field and wish you could go out there some code that you can't really replace, you know. But in this case, no, this chip comes from the factory with that capability. So it's really cool. Going down, we're almost done with the first page, I think, here. The expansion connectors, only thing to mention about those is they've got a number of pins on them. Well, I guess we should talk about them now, because I don't think I brought a separate page in the PowerPoint. They're mentioned on our docs page. So I'll real quick flip over to docs. We kind of breezed past them, but you know, they let you connect expansion boards like this little one with whiskers here that we made. That's just a couple of micro switches connected in. So you can see the pinouts on the schematic that show you, like pin 1 is marked with this little triangle here. And then we're just connecting into to power and a couple of IO lines, or actually I think it was just ground and a couple of IO lines. And we let these micro switches tie 1 or 2 different GPIO pins. We could enable internal pull-ups, and then they're just gonna be tied to ground based on which one is, or both, is activated. So that's what that is. These little circuit boards, I've got a link also in a later slide to show you where you can get those. They're real common, these little proto boards. But yeah, that's what the expansion connectors are. It turns out what we did was we duplicated them. Each of these expansion connectors have an identical set of signals on them. They're put in a reverse orientation. So if you had a board that hit all of them and you flipped it 180 degrees and plugged it in, it would work exactly the same. Also, it means you could have two different little separate boards, and they each can do all the same things. So that's what it's all about. That. So let's flip back over to. So that's those two connectors right there. It brings over I2C or I2C bus, which is just a serial way for a computer to talk to peripheral. Now is the Wiimotes. You know, the Wiimotes that you connect to your Wii back in the day for Nintendo. Those are I2C devices. But there's a lot of stuff that's on circuit boards that's connected this way. Another super common way to connect things is called a SPI bus, a serial peripheral interface. And it's that bus is also brought out. That's this SCK, so it's clock, and then master in, slave out, master out, slave in. Obviously 3.3 volts regulated, which we'll see the power supply in a second, and ground are brought to the connector, as well as raw battery voltage, which obviously varies as the batteries are fresh and then go back to dead. But 3.3 is regulated. It's always going to be nice and solid. So that's really everything on the expansion connector. You get your USB interface, little transient suppression, which is in case it's like suppressing mainly ESD, electrostatic discharge. That would be people's static electricity shock and stuff like that. So we're trying to protect the USB against that. But it gets wired straight over to the processor. It's capable of handling the USB interface on its own. And the last little thing on here is this little voltage divider here with a couple of 100K resistors that lets us monitor our own battery voltage. So when you talk about in the CodeBot read its battery voltage, look in bot core where that's done, and you'll see there's a ×2 thing going on there because this is a divide by 2 battery voltage sensor just leading over to an analog to digital converter on the processor. So the second page, and man, Amber, I tried, but it's already been over 30 minutes. So all right, how's the speed? Thumbs up, thumbs down, middle, right? Just right. Okay, well, all right, good. Okay, we'll find out when we let everybody talk, right? So so you can see our LEDs, our user byte LEDs, what we call the operation specific LEDs, which is like all the line sensor emitters, the proximity sensor emitters are now indicators, and then the power indicator. All of those are controlled. Even the little power indicator that's over next to the on-off switch is all software controlled. So so you get to blink it on and off if you want to. It's only in a later project that we actually, I think it's all systems go, we finally say, okay, why don't you blink that and blink it at a different rate if your batteries are weak, you know? So there's lots of things that you're kind of have to create yourself with CodeBot, which is the whole point. So those LEDs are, we could have hooked every single LED up to a pin on the STM32 and just, had a separate port pin on the STM32 for every LED. That would have been simple. Why didn't we do that? Well, going back up here, we ran out of pins. So we used all the pins on this part, and there's not a bigger one in this flavor. This is, I think, a 64-pin part. So so we kind of had to do something else, right? So how do you expand the number of output pins that you have? Well, one way to do that is with a serial interface. In this case, we use these shift register chips. So I'm going to pull up the this STP16 part. And I've got it right here. So if I go up to the top of the page here, so it's another ST part. It's a 16-bit, and it's not just a shift register. And how neat the little font is here! Wow, it's not just a shift register. It also is designed to drive LEDs, so it can sync current, and it can sync a constant amount of current. I don't know why the font is so weird on this. It wasn't that way before. So okay, hopefully that won't plague me too much more. If I scroll down to where we were, I kind of pulled up a nice page that shows you an internal block diagram. So internally, there is just a 16-bit shift register, which has a clock pulse input, a serial data in, a latch enable, and an output enable. So those are kind of the 4 pins. And so as you put a binary 1, so logic high on here, and then you pulse the clock. So on an edge of that clock, it's going to clock into the shift register. And it's going to shift each bit that you clock in across so that you can control 16 LEDs. So you sort of do a burst of 16 little pulses of the clock and set SDI, serial data in, high or low, and now you've set up all 16 LEDs, right, to some value. And the current is programmed through a resistor. So there's a resistor that sets the current on these things. The schematic tells you what that is. If you wanted brighter or dimmer LEDs, there's a resistor here. So this one, R8, on this top guy is 10 milliamps per pin, and R14 on the bottom one sets 20 milliamps per pin. So go to the data sheet, figure out what you need, change that resistor out, and you're good to go. You can make the LEDs as bright or as dim as you want, although these LEDs can only handle so much current, so you might want to check that too. So anyway, the shift registers these are wired up in series, so there's a cascade serial data out that cascades from this one into the next one's serial data in. So altogether, we've got a 32-bit shift register, we've got clock, latch enable, and serial data in. And then there's the output enable pin as well too. On this guy, which is controlling our user LEDs and our indicator LEDs, that's just set by the processor directly. On the other one, it actually is set by a PWM pulse, so we can actually pulse the proximity emitter. So the proximity emitter LED, which is somewhere on here. Oh, it's right here, our RF prox driver. You can see how it's wired to multiple ones of these outputs. So the more outputs we turn on, the brighter it gets. So we can control the brightness of this guy. And in fact, it can handle, LEDs can handle really powerful pulses of light as long as you don't leave them on continuously. They can handle a lot higher current in pulse mode than they can in continuous mode. If you use bot core, we prevent you from setting it. But if you're directly manipulating these, there's one little warning. I think this is the one thing that you could probably break if you tried hard. You'd have to replace this LED if you did, would be to turn all these on and leave them on. And then, oh, you're not pulsing this guy, you're setting him a continuous current that's higher than he really is rated to handle. He might survive it, but it's not recommended. So take a look at that before you play with the prox driver. Everything else, though, play with your heart's content. And this whole shift register thing, currently, if you've got a CodeBot, it's controlled down in BotCore, and BotCore actually uses an underlying library that uses a SPI peripheral, a serial peripheral interface piece of hardware that's inside the STM32 to control those really fast. So I think it's clocking it at 10 megahertz. So it's clocking it really fast. So nearly instantaneously, you get, a 32 LEDs set. But when we first brought the board up, we did it fully in Python. We just used MicroPython, and we made a little bit bang routine that bangs these guys out. And I've actually got that code on a PowerPoint slide here. Actually, I'll bring it up right now because I'll never remember to later. Yeah, it's right here. Bit banging LEDs. So this is the original bot core code that did this. We set all these pins, B9, 10, 11. These are set to latch enable, output enable, clock, serial data in. Right? We set up that proximity emitter. And then, so there's an enable and a write in this little LED driver. So enable, just the output enable is active low. So it says not to do enable. So that's the Python for the active low thing. Sets our pulse width percentage to whatever the duty cycle is set by default. And then the write function is kind of the coolest function because it's actually this little 32 count for loop is actually shifting each bit out. It's strobing the clock, brings it high, brings it low. So it sets the data value, and then it strobes the clock and shifts that value. So you tell it a value that you want to write, and it shifts all 32 bits out. So there's a bit banged serial shift register, which this would be a great, electrical engineering class for, for microcontrollers or something like that, just to show how you do this. It's really cool. But yeah, in BotCore, it's all done for you. The next step after this was using MicroPython's SPI libraries. So you could go a lot faster using MicroPython SPI libraries. And then the next step beyond that was building in a C module that handles all of this into the bot's firmware, which is where it is right now. So that's a little bit more about those LEDs. The push buttons are simple. They're just wired over to, one of them is actually the reset line. So it's the real reset line of the processor that truly resets it. The other two are just user configurable buttons. They're internally pulled up. So you have to enable the pull-ups on those pins, and then you can, they'll be pulled to ground when you hit a button. Here are the line sensors. These guys are these QRE 111 or 1113s. Those are up here. So there's the data sheet for those guys. It's a classic part that people use for robots and stuff. So it's a great one to use. But you can actually see where we stole the picture for our little docs. It was right there out of the data sheet. But that's what that is. And so you got your emitter and your phototransistor with a pull-up resistor on all those. There's your 5 line sensors. also they go to analog capable pins. So you can actually do either analog or digital reading of those line sensors, which is kind of cool. The proximity sensors are these TSSP 4056s. They're actually, and those are on here too, I think. Yeah, those are made for, they're like the kinds of things that would be in, like Vishay makes a lot of stuff that will go in remote control receivers for devices in your home. So you can certainly use this kind of device for that. The 456 is 56 kilohertz is what it's tuned for. There's also a 38 kilohertz version. We use the 56 for a reason, because we wanted to do something a little bit special with this. Vishay had put out an app note a couple of years ago about using these things for distance sensing, and you can do that by modulating the frequency. So we don't always just use them at 56. They're most sensitive at 56 kilohertz modulation of your IR emitter, but if you sweep it down, you can gain some additional levels of granularity in your distance measurement. So it's really interesting. You can look in BotCore to find a little bit more about that. You can also just use them as on-off detectors, you know, and see that but it's an infrared receiver, is all this is, with some amplification and stuff in it. So that's what that is. Actually, here's the diagram. So there's actually a decent amount of processing that's done in these things to be able to do as good of a job as they do at being sensitive, and yet not too sensitive to sunlight and things like that. All right, so those are the two proc sensors. We talked about the emitters over here. The wheel encoders are just discrete phototransistor and a photo emitter, or an LED, that is. And that's all those guys are. Then there's the accelerometer. You can see the accelerometer is not a lot hooked up to it. It's a tiny little chip right in the middle of the bot. It uses an I2C interface. So all it needs is clock and data over to the processor, and you can talk to the accelerometer. It's an LIS2HH. You could do a whole course on the accelerometer. It is amazingly awesome. There's a ton of stuff you can do with this. You can shout your name at it, and you can, if you read samples fast enough, you can plot the voice waveform that comes off of it. So you can even use it as a microphone. Never done that, but I've tested that on an oscilloscope. It's pretty cool. I can do a lot of stuff. So there's one library over in, besides the fact that BotCore, uses it, BotCore uses this LIS2HH accelerometer driver, which we wrote. And if you want to see, if you want to cheat and look at how we did it, it's all in Python. So we're completely just using MicroPython. We're defining all the registers from this same data sheet that I was just pulling up. But we by no means exploit all the features of it. So there's other features you could use. But as a advanced student assignment, you could say, hey, you can't use BotCore. Here's the data sheet for the LIS2HH. Go find out the orientation of your CodeBot. Well, it's doable. This is exactly what BotCore does, right? We're actually using the MicroPython, write to and read from calls for I2C. So this is really cool. So that's the accelerometer. So what else do we have? We're almost through the schematic. Last page here, there's a power section of the STM32. So that's just where we hook power up to it. Nothing exciting there. And then the power supply is the last bit. So I remember pointing to you hey, here's the little switching power supply, and there's that little big chunky rectangular little cubicle thing that's the inductor. That's actually the power storage element in combination with this capacitor here. And I don't know that we'll have any students that really care about how the 3.3 volt regulator is done, but it's a whole science in itself, and it's really neat how that works. And it's a very highly efficient way of converting the battery voltage into regulated 3.3 volts. So we don't have to talk much about it right now, but I would love to do a whole session just on that. But it's called a synchronous buck regulator, because it's bucking it down from the battery voltage level to there. There's the power switch. One more other little cute thing, if you put the batteries in backwards, it won't hurt it, because we've got this reverse polarity protection. Otherwise, sometimes micro circuits don't like being hooked up backwards, but this little FET will only turn on if the gate here is biased in a positive way compared to the source. So that's how that works. Similar sort of FET used for the USB inrush to limit, when you plug it into your PC, there's a limit to what USB devices are supposed to draw when you first plug them in. And there's lots of capacitors here that bypass, give you, regulated voltage on all the little components, and that's what these are. So whew, went as fast as I could, but that's through the entire schematic. That's everything on here. And I think that takes us to close to our Q&A time. Oh, before we do Q&A, I just want to mention the expansion. We talked about the expansion header. A couple of folks have asked, where do you get those little boards like the one you had there? SparkFun sells them. They're available from a lot of different places. I actually grabbed this one off of Amazon, and you can get. There are ones that are cheaper than this, but we can get whole packs of these things for 13, 14 bucks. And it also comes with the headers that you can solder in, and the expansion headers were made to fit 0.1 inch spaced boards like this, and 0.1 inch headers. So that's what that is. And then I mentioned the UART connector. So it's a 6 pins. This is not a great picture of this from SparkFun, and also on Amazon there's clones of this, but there's a little USB to serial port thing. So that UART port, if you buy one of these little boards and it's got a little socketed end connector here, you can actually plug that straight into the top of that. If you solder in a header, plug it straight in, plug a USB cable in there, and you'll have a console port. You'll have another REPL. So it's like a second REPL that's not dependent on the web browser, using CodeSpace. So it's kind of cool. You could also use that UART port for controlling external peripherals too. And then the debug connector that's labeled debug on the CodeBot is actually what's called a JTAG port. But we're using, and it's a way to do low-level debugging of what I made a comment here. It's the physical machine, not the virtual machine. So CodeSpace is really cool because it lets you connect into a Python virtual machine and single-step debug and look at things inside the virtual machine. But if you want to look at things inside the physical machine, you need hardware support. And so this is what gives that to you. So ST sells these boards. They're super cheap. It's like $8 or $9 off of DigiKey for a discovery board. You can also get really cheap standalone debuggers. But we made the pinout. There's a little 6-pin connector on this discovery board. All the discovery boards have a built-in debugger. We made the pinout identical to that. So if you buy a little ribbon cable that connects over, you can just plug in from this to your CodeBot if you wanted to do really low-level debugging of C code on the bot. That's what that's all about. So that is it for the slides. So 47 minutes by my count, Amber, for future reference.
Not bad.
And that's with no stories.
Not a record, but not bad. Yeah,
that's with no stories. Hopefully I didn't set any bad speed limits or something. But anyway, so let's open it up for Q&A. If we have any questions, I'd love to answer them and hear your comments and feedback.
Yeah, and please feel free to turn your video on as you're asking a question. It's very awkward to talk to yourself.
You have to allow us to start our video. It says the host has stopped it. Can you hear me?
Yes, I can hear you. What? I'm sorry.
I can't turn the video on. Unable to start video. I got a dialog box in Zoom. Unable to start video. You can't start your video because the host has stopped it.
Who's talking so I can turn you on?
Oh, I'm Ed Bujak.
Okay, Ed.
Yeah.
There you go.
The host is asking you to start your video. Start my video. Okay, that's me. So I seem to have heard that it's you have an IR sensor, but you also have proximity. Do you have both? That mean for distance?
Yes. So these little front-facing sensors here, they are infrared. Those are those two Vishay infrared sensors.
IR, right?
And so those are what we're using to sense proximity.
Oh, for line followers, say.
No. So the line followers are underneath. So there's 5 line followers here.
Yeah.
That have a photoreflective switch. Sorry, I just swallowed water down my lungs. But yeah, there's 5 infrared. There's actually a lot of infrared on here, right? There's the 5 photoreflective switches, those QRE 1113s, and there's 2 of the Vishay, the really kind of super fancy, Vishay sensors for distance, and they can measure approximate distance out to a couple of meters if you're lucky. We go into that a little bit, and then and there's a discrete emitter here, and that's the thing that you can really power up and get a very bright long distance light on that as well. So, and the other infrared stuff that's on here are the the wheel encoders also have infrared LEDs that shoot across and make a photo interrupter.
Great, thank you.
All right, David, Victor would like to know if you flip the JTAG cable and insert, will the student damage the board?
On the JTAG, I don't think so. It doesn't look like it would. I haven't tried it, but it would put 3.3 volts on a no connect potentially. So I don't think that would be a problem. It is one of those things I would maybe rarely do with students unless they were super advanced. But because even like a lot of times when I'm writing code for the core, like I'm making changes to MicroPython, I'll just update it over the USB. I don't even plug into that debug connector anymore. I just like I use the firmware updater and put new code in that way. But it could be handy for doing, like if you're doing some special projects or something. But yeah, I don't think you're going to damage it, but you never know.
All right, anybody else?
Hello, this is Victor again. Can you hear me?
Yes.
Yeah.
Okay, great. Good to see you. I had to get off because a student was actually trying to do some Onshape coding. There you go. And sorry, I'm only typing with my left hand because I broke my clavicle. So if I have this typed in chat, it's because I'm typing with the left hand kind of quickly. So I'm expected here in Austin to maybe do some remote learning in the fall as well. So I'm kind of envisioning what we currently have with code labs and how to stretch the curriculum. And that's why I'm really appreciating this electronics, schematics and stuff. But since I also teach Onshape, which is a CAD program language, or just like Autodesk Inventor, I can see kids looking at making learning the terminology to create a electrical schematic. Not very fun, but maybe just for a couple of days they can do that. So my question is, number one, data sheets. Since I moved, are the data sheets for the specific parts downloadable from within your IDE?
No, we did not put the data sheets up there because I think we would potentially have to get like distribution rights for them or something like that.
Okay.
I'm not sure. We probably wouldn't get in trouble because the silicon vendors want you to use their parts, but it's really easy to find those data sheets. If you Google any of these part numbers, you can download them. So you can make your own collection of them.
Yes.
Yeah. So yeah, we didn't make them linkable though.
Right, that's fine. Which I've done before. You go to this vendor in Colorado or another vendor in New York, right, and download the Chinese data sheets and let them read through that and then actually make a CAD part and say, oh, that CAD part dimension is the same thing as the one that's on the board, right? So, okay.
Yeah.
Fair enough. I'm trying to stretch out these products here. Also, on the microbit, do you see an easier way to flip it between the hex files? Because sometimes I'm using it like, let's say with students on 1 week for remote learning in the fall, they could do some emulation software using CodeHS. And if they get to a certain point, then the student can get the microbit within the school emailed to that local zip code. Do you expect to see any other emulation enhancements? If the student breaks their hardware at their house, and therefore they have to go to maybe a more enhanced emulator?
So I think is the question, or have we thought about putting an emulator inside of CodeSpace so you don't have to have the physical hardware?
Oh, okay. Let me rephrase it. So, so here's my here's for another class. Here's my microbit with a like a SparkFun extender cable with a button, right? And but this, let's say it has a battery pack or have another sensor. I know that the CodeHS does not have all the sensors that are available from other vendors. So I'm trying to find out, is there a way to either pull in an emulation of a different sensor? Say a VCSEL laser, right? A VCSEL laser rather than a ultrasonic sensor.
So
Todd
I
wants to
wanna make-
answer this one for you.
Yeah.
Let's see if he'll
Okay.
jump on.
Oh, am I talking?
You're talking.
Okay. All right. So we
Why don't you
did.
introduce yourself first?
Yes.
Yeah. So, sorry, I'm with Beria. I've been with the company for about a year and a half. Senior design engineer, and
And the hero with the teacher dashboard. All you teachers,
Yeah.
you can give Todd your high fives.
I just said to Amber, in November we did a series of blog posts that was how to integrate different sensors, and we went through. Most sensors communicate very similarly. So it's either like an analog or a digital interface. So we made a series of blog posts that talk about integrating different sensors and how you would do it with an analog sensor or how you do it with a digital sensor. So we can get you a link to that. Be a good starting point.
Yeah, that's fine. So like I was mentioning before, I have other, because I'm an engineer by profession. This is my 7th year teaching robotics and CAD. And so I have different types of, gimmick tools, right? Different types of little pieces. And I know like for my intro to CS, remote learning, I might be using a motor, right? For my 3rd or 4th year, okay, now they're a little bit more advanced. And maybe I need to use some of these other diodes, right? A 2222 with something else, a little FET. But I want them to maybe hook up to the CodeBot somehow, which I don't have yet, right? I don't have that yet, but I'm envisioning how can they do this remotely in an emulator rather than giving them parts at someone's house where their cat's gonna lick it up, they're gonna lose it, they don't know how to hook it up, so I'm trying to think of a way to whether was that can be done inside.
Yeah. So Victor, let me answer you very directly. We do not support any emulators right now. It is something that I'm being told to start my video. So it's occasionally talked about, but right now, just cut and dry, we don't have any support for emulators at this time. Getting
That's fine. I just want to know so that I can know how to recommend how to use the current tool that I have and to manage parents' expectations. That's something to know.
Yeah, we really thought hard about it, especially with COVID and stuff. We thought, man, we know what we would do, so we've got some ideas, but then there's so many advantages to having the physical product in your hands that, and it's really nearly impossible to emulate everything that's going to happen, on a real units, right? So it's this big trade-off, and we're like, we'd be better off focusing on trying to get the hardware to the students and letting them actually experience the real thing. So.
Right, and that's why I was asking about the JTAG, because if we hand it off to someone and then their mom or their dad say, oh yeah, you hook it up this way.
Yeah.
Right, and then they're in the water, and then it's okay, well, everyone else is proceeding, and then how do I let this kid who has a broken board proceed? I guess it's something for me to just think about some more what's the other option?
Yep.
Okay, thank you.
Sure, thank you.
All right, who's next? Dan, you woke up at like 4 a.m. to be here.
Yeah, Dan, say something.
Surely you've got some questions. I won't even turn your video on if you don't want me to.
No, you're good. You're good. Yeah, it was a little bit of an abrupt start to the day, especially jumping into the schematics.
Yeah.
Good
Sorry about that.
morning.
No, but thanks. That was a very in-depth kind of, whirlwind of an overview, which has left me with some good things to think about.
Awesome.
Good. Yeah, and I guess we just had, maybe we bit off a little bit more than we should have, just, deciding, okay, in 1 hour, we're going to try to cover the entire thing. We definitely could have broken it up into multiple sessions. So if you have suggestions for other pieces that you'd like to learn more about, or we're always looking for, we need to put more content on our blog and stuff. We've got tons of ideas. Our engineers are super busy doing all kinds of things. Some of you probably know we do IoT consulting work in general. So we're working on all kinds of cool projects. And that's one of the things that I think infuses into our educational curriculum and our products too, is we do this all the time, and we really are passionate about the technology. But we want to find things that you as teachers out there with the students that you want to know more about, and we're more than willing to go into depth on any of those areas that you find interesting.
Yeah, I wanted to remind everyone, because I know that we have some newbie coders in the group, and I know that not everybody was on when you spoke about the different levels of what we do with CodeBot and all the coding. It's just a reminder that this is advanced. As far as something that would be in the school, this is not, you're not expected to even understand what all David said today. What we're trying to bring to schools and learners everywhere is a very easy entry, as those of you who are just discovering Jumpstart to Python, a very easy entry into coding, but offering a lot of depth within our products, so that folks like Victor, who spoke earlier, we've met him and we happen to know a lot of what he's doing. He's doing a lot of advanced things and a lot of in-depth things with his students, but that's not where you as a beginner need to be. So it's a, what do you call it? A low entry, very high ceiling product that we have here. So please don't let this time intimidate you, but it's also an opportunity for those of you that are beginning to be able to communicate with others, maybe in your district, if not in your own school, where there may be some more in-depth classes. You can direct them toward us, because there is opportunity with our products to go in depth and get pretty advanced. So.
Yeah, thank you, Jerry, for reminding that. Because I did, when Amber and I were talking before the call, we talked about it, and I said, please make sure you warn everyone that this is not, I don't want anyone to be intimidated by this. In general, our stuff is actually very, very approachable, right? I mean, we've got, very, very young kids doing code space, and so we don't throw you off the, off the side of the bridge or into the deep end, right? But one of the things that when we talk about what makes Feria Labs different, like how do we want to, what are we doing that that gives us, a reason to be out there among all these other ed tech companies? And one of the things that we want to make us different is authenticity and seriousness about what we're doing. These aren't toys, but it's fun. I mean, what we're doing is awesome, and it's approachable to anyone. When we published the schematics to CodeBot, it's something I've been wanting to do, and we just hadn't got around to it. But putting them out there, I felt so good about it, because a lot of you aren't old enough to remember this, but as a kid, I'd like crawl behind the television set, and of course I was like this as a kid, right? The big console television set, and pull off the cover, and there was a schematic diagram on the back of this, this brown particle board cover. There's a schematic. It used to be, the vendors would ship schematics and things like that. So, it was wild to me, because as a kid, I would look in there and go, all these parts, it's like magic, but it's not magic. There's this piece of paper with this stuff on it, and if I learn enough about this, I'll know everything about how this works, And so I think kids these days need that so much, and I want them to see that that's there, And so I think, to me, just that this is all kind of part of the continuum of how we want to do this. So even in the very simple parts of what we do, we're not babying the students. We're telling them always we're connecting it to the real world, stuff that impacts their lives every day. And so hopefully it'll be not scary, but it'll be exciting to you guys going, you know, I think I probably could learn all about it if I wanted to. I could dig in and learn everything about this. Man, I wish I had the time, you know. But another thing that's cool, we can talk about another session maybe, is how would you design something like this? And so we actually used open source tools to build a lot of this, like KiCad is the CAD package. So if I were doing a student class like in high school or something, I'd have them design a board. You know, they could design their own expansion board using the same exact tools we used to design CodeBot. And that's, you know, that's actually not too bad, not too expensive to get one built. So I'd love to see that. Yeah.
Yeah, I'm going to interrupt you a little bit. Terrence, did you want to chat? You said maybe David has answered your question, but feel free to go ahead and pipe in here and talk to him about the expansion board. Or expansion. Hello, Terrence.
You scared him away, Jerry.
Not allowed.
I can be heard now, right?
Yes.
Yeah.
All right. So can you also see, so you have
Yes.
that board that you have the whiskers on.
Uh-huh.
And you mentioned the S word, soldering and things like that. Not going to happen at my school or any school I know of. I need that bridge though. That expansion, I need that. That's going to be a part you guys sell at some point.
Yeah, so that's interesting that you say that. So you think, and this is something we've got a little roadmap of expansion boards to do, and we're like behind. We need to do that, especially the simple ones. And that would be a super simple one, just a board that already had the header soldered onto it, and maybe a little piece of white plastic breadboard on top, so where you could plug in components. Is that kind of what you're talking about?
That's all I ever needed in my life right now.
Okay.
It is my most desired thing because I think, of course, now I can get to anything almost, and simply that would be cool. Otherwise, I'm dreaming of ways to plug things in and figure out how I can add a radio receiver to it, and you know.
Yeah, that'd be awesome. We've thought about that too for things like we're planning more like algebra and stuff. You know, the algebra with robots. It's also late incoming, but it's still in the works. And you know, some being able to add on components like that, you can do some really interesting mathy things to make it real. You know, like.
And I'm not gonna teach anything lower than algebra 2 until you do. If I can get a bot to do this algebra, then I'll step down to algebra. I'm good with that. I need something to keep the kids engaged.
Very cool.
Otherwise, excellent, and thanks for this. This was very enlightening.
Yeah,
and helpful.
thanks. Appreciate it.
Louise is gonna volunteer to make your whiskers for everybody since she solders in with her students.
Yeah.
All right. Anybody else? Kuldeep, did you want to ask a question? All right. We'll stay on for a few extra minutes as everyone logs off. So if you have any other questions, you can stay on the call or just email us at your convenience.
And while we're waiting, I guess, another thing we're going to do, and Amber and Jerry, keep me honest here, because I've been saying I'm going to do this for a while, and it's just, you know, sloth is what it is, or maybe not doing it. Slothfulness, I guess. The 3D models for like the STL files and stuff to print these little visors, because you can make your own visors. The visors, the whole point of these things being on here, they snap on top of those little Vishay sensors, is to block out ambient, like even some fluorescent lights have a lot of infrared in them, or some of the LED lights have a lot of infrared, and they'll just really wash out the sensor. So you get a lot better range on your sensors by putting these visors on there. Plus it protects those little through-hole sensors from getting bent back and forth. So that's what those are. But you can, there's holes in the board, and there's a contour in the board so that you can make 3D pieces that can snap on here. So one thing I want to do, we'll publish those models, but also we want to publish this the step files and the files for the board outline itself, so that you can, if you've got I know schools have a lot of 3D printers. I'm not sure if they do, like a lot of schools we've been to, I don't know if they do a whole lot with them, but they have them, and this gives you an excuse to do some really cool stuff. You can make like if you want to do sumo robots, we've got all the sensors and everything. You just need a blade for the front of it, right? So you can make a sumo bumper to be able to go and do that kind of thing. So anyway, some good ideas there. We'll definitely put those out there. And if we don't, it's all Amber's fault because she didn't make me do it.
Well, in the Bronx, that's exactly what we're after. We need the kids. The first thing they want to do is robot wars, where they can push somebody out of the ring, and they don't care. They want to do line following and all that cool stuff too, but they want attack mode robots because it's the Bronx.
I went straight to the
That's
saw.
what happens.
Yeah, that's what I do too. I love that. I mean,
Wars.
we wanted to make it sumoable, and they definitely are. So
Yeah, they are.
Yeah.
They definitely are. But being able to encase them and protect the parts is kind of kind of the next. And we have those 3D printers, and nobody's really using them for what they could be using them for. So files will be helpful. And yeah, because we got to just sort of figure this out for the remote as well as the in-person.
Yeah.
Awesome.
Yeah. I think with remote, I mean, it makes everything hard. But we've talked about that some with like, how do you do robotics things? And you can come up with a set of robotics challenges that people can do remotely, like even sumo. You can set up, if you got a little 3-foot area, you can tape, do a line of tape and then put you a Coke can in there or something and see how start a stopwatch. How fast does it take you to, how fast can you knock that thing out of the sumo ring? I mean, that's a way to do that sort of thing, even if you're remote from all your other friends, So,
oh man, you're a gem there, man. That's going to be great. I mean, people have this. They're pinned in these in the foxhole now, and so they're looking to see some action. So,
cool.
Yeah, another thing to put on my list. I'm going to do the refrigerator thing. I'm going to record that. The two microbits reporting temperatures to one another, and now you've given me bull in the ring. There we go. We'll call it bull in the ring. That's going to be.
I love it.
I got to figure out how to dress it up, maybe, or maybe even not. I do really love the way this thing looks. I wish it had 4 wheels sometimes, but I'll get over that. Horns, there you go. That's easy enough. I can do that with some tape, maybe. I'll figure it out. It'll look good. It'll look good when I do it.
David, Victor just put another question in the chat. Is CodeBot using Python 3.6? Does it recognize 3_000 instead of 3,000?
It's using, like I said, I think it's 3.4 was the version of Python that MicroPython is at right now. But we can double check that, and I'm not sure. What was the question about the underscores?
Victor,
Hi, this is Victor again.
Yeah, go ahead.
Let me I can't find my face. Where to start video? Okay, great. So I'm trying to again extend my curriculum here. I know we just deprecated with Python 2.7, right? So I'm trying to show some of my kids. Okay, maybe one day out of the week, we're gonna have some old code, say Python 2.7 code that they need to update to 3.6 or 3 point something.
Okay.
Question is, can we do that with the with the next year's IDE? Can you flip between versions? So like 3_300 is one way to say 3,000, but that's only a new syntax that can be used, I think, in 3.5 or higher. But you couldn't say 3_000 in Python 2.7. It just give you an error. It'll say, I don't know what that means.
All right, so I don't know if you can see am I still sharing a screen?
I can see your screen.
I just
tried it. So I've answered both of your questions on the CodeSpace has answered your questions here. So the first one is 3.4 is a sys version. So if you're ever on a Python machine and you want to know what version am I running, import sys and then you do sys.version. So we're at Python 3.4, and then the underscore trick looks like it does work for 1,000. So yeah,
okay.
I didn't even know that.
Yes, I'm trying to get. So the intent is, if I see any old code, this I can't. Yeah, that's all I need to know. So we're running 3.4, and if I see other code that's 2.7, they can learn how to fix the errors to make it work in CodeLabs. Thank you.
Yeah, awesome. Good.
All right. Anybody else? There's no new questions in the chat box. So if everyone's been sufficiently entertained or overwhelmed with information.
We're past our time, so I think we're good. But definitely send in your if you got suggestions for another one or something, we'd love to do that, and just let us know which way you want us to go, and we're trying to do the right thing for you guys.
Yeah, for my students, I want to see, the stories of the applications to what they're learning in class, to what, Feria is doing for its clients, and get some of those recorded so that you can share them, because they're great stories and the kids need to hear it.
Okay.
All right. Goodbye, everybody. Have a great night.
Yeah. Thanks, everyone.